Cool. Hello. So I'm Tom Svillans. This is Paul. We're both based at CETA in Copenhagen, and we will be presenting our paper on entitled "A Multi-Scalar Approach for the Modeling and Fabrication of Freeform Glue-Laminated Timber Structures." So just to provide a little bit of background about us and where we're coming from, both of us are PhD researchers, part of the InnoChain training network, and that is a research training environment that includes 6 institutions and 14 industrial partners across Europe. So there's a strong focus on industry collaboration and applying research to projects and sort of real situations. And one of the main themes is feedback in the digital chain, so how the sort of linearity of the design to fabrication chain can be disrupted and reconfigured through various different topics and research subjects. So within that larger project, InnoChain is divided into 3 work packages which address different themes. So my project is entitled Integrating Material Performance in Freeform Glue-Laminated Timber Assemblies, and it's part of the Communicating Design work package, which sort of challenges the separation and discretization between knowledge domains by proposing new links between various domains of knowledge in the kind of architectural design and fabrication process. And that's supported by partners, a partnership with White Architects in Stockholm and Bloomer Lehmann in Switzerland.
And on my side, I'm collaborating both with Bureau Rapport and Design to Production. And my research project is entitled Multi-Scalar Modeling for Building Design, and looks at data exchange between different scales and resolutions during the design process of large-scale architectures, both during early and late design stages. So we will start introducing what is multi-scalar modeling. Probably most of you have seen this short movie from Charles and Ray Eames, during which the camera zooms continuously in and out from a quiet couple picnicking inside a park to the scale of the universe and back through the skin at a molecular level. So the question that is raised here is how do we transit between the different skills during a design process? And this is also a topic that is looked at in other scientific fields. Basically, this topic comes from the realization that the full behavior of a system cannot be represented within one single model because the level of detail differs from one scale to another. So for example, here in this image, this is a global environmental model that simulates a tropopause folding event, which is when different layers of the atmosphere are encountered together. And of course, you don't want to simulate this for the whole Earth, but only at a localized, at a specific location, and how these influence higher levels. There is an existing architectural design project that deal with multi-scalar modeling and try to transfer the information between different scales from material specification and robotic fabrication through a more global design environment. This is the Stress Skins project that was realized at CETA. We are particularly interested in looking at larger and more complex building designs where there is a lot of different layers of material that have to interact within each other. And it's sometimes very difficult to set up a continuous integrative computational design workflow. So we believe that breaking down such complex geometries into different levels of resolution can ease the handling of their design process. You can see actually, you can look at wood as a multi-scalar material when you think that the fiber layouts of the smaller scales impact the structural performance of larger elements and assemblies.
Yeah, so today in the timber industry, we see it operating at quite a large scale and high rate of automation. These are some examples of sort of state-of-the-art projects right now in complex timber manufacturing, we would say. So that goes to say that engineered timber has allowed very new and exciting timber building components to be invented and developed with. So this is Nine Bridges Golf Club of the top left, and another Shigaroban project, the Pompidou Metz building, which we saw just a second ago, to the right. So the material system here is obviously free-form glue-laminated timber, or glue-lams. And this presents us with kind of an opportunity to, a good opportunity to apply this sort of multi-scalar modeling approach to, because if you consider all the steps and different sort of resolutions of a material, larger design scales, you end up with a very sort of varied spectrum of scales. So here we can see some of the steps and scales involved in the Pompidou Metz project, for example. So moving from sort of the broad design-led network surfaces and down to the component level, then to the glue-lam blank level, and then to the further on to the processing and assembly kind of scales. So what that means is, if we look at glue-lam as a sort of multi-scalar engineered product, what a glue-lam is essentially is an aggregation of smaller lengths of timber from which all the defects have been cut out, which are pressed and formed either straight blanks or curved free-form blanks. So this means that the composition and making process of these blanks is tied to the geometric complexity of the required design element, which means that different types of glue-lams require varying degrees of fabrication complexity and material usage, depending on whether they're linear, single-curved, or double-curved with twisting. So then there can be this relationship between the glue-lam type and composition and the broader design objectives and requirements. So there we see this kind of link between the two scales of the material system and the larger elements.
So we have been working on the design and realization of, or partial realization of a demonstrator, where we could address the different challenges just mentioned. So we started from an abstract network or graph that defined the food condition and extended the design workflow, where we were able to map a simple branching pattern onto a global structure, and onto which we could map also the each single glue-laminated timber elements. And the same graph helped us to generate and localize particular components during the design process.
Yeah, so this graph-led approach allowed us to kind of keep the relationships alive between sub-elements, and which allowed us then to further kind of zoom in on each element more specifically, while retaining sort of relationships to the broader model. So it also raised the question of how to model these relationships between the overall design element and glue-lam composition. So this led to the development of some software tools that allowed us to quickly look at the material specifications of individual glue-lam elements. So on the top you see a curve model that is driven by the higher level graph models, which starts to define curvatures and element positions and rough geometries. And then on the bottom you see the kind of relationships between seeing individual lamellas from each blank kind of out of a glance, while still retaining a relationship to this kind of higher level model. So what the bottom image is showing is actually each lamella in each glue-lam being tested for material bending limits according to some specified ratio. So it allows us to kind of swap very quickly between very low level material data and adjust at a higher level as well.
And then we started finally mapping the different levels of resolution that we had to deal with, from the high-level global graph providing us fabrication information for each component, lamella size, thickness, to the corresponding fabrication space. And all levels could communicate and interact between each other through means of feedback, where, for example, the spring-back factor of the physical prototype was measured through scanning process and taken into account the next fabrication iteration.
Right, so this diagram just reiterates that idea of feedback between scales, which basically means that constraints at lower scales could start to bubble back up and affect the higher scales. So most notably here for us was constraints in the material model, especially in terms of lamella sizing. So changing or constraining lamella sizes affects how curved the glue-lam blank could be, which therefore affects how closely the fibers of the timber blank could align to the beam element axis, which then goes on to affect its kind of structural capacity and therefore might force a reconsideration of the element's role in the larger model. So this approach went all the way down to the fabrication data. You see on the left the blank and beam geometries, the surfaces for machining, and even kind of tool bath generation. So it was this kind of ability to spot challenges or risks at the fabrication level while simultaneously manipulating the overall design, which allowed a flexibility and adaptivity that would, I think, be tougher with other more linear design processes. And that fed through also into the making of some molds for these things. So as another sort of scale within that fabrication process of looking at how the molds we make, what are the difficulties there, and how they can feed back into kind of a more intelligent design of for example, a beam member. One particular behavior specific to laminated wood is springback, which we had to compensate for in some cases. So this was an opportunity to look at this and how this could feed back, how we could feed this kind of material behavior back into the mold models, in this case, which had to overbend the glue lambs by certain factors to get the desired result in the end. So combined with 3D scanning, this let us adjust mold models based on previously made elements, as Paul just mentioned. So here are some photos of some of the prototyping. We took some of these elements through to fabrication to try to test the feasibility of the whole process, but without kind of proper pressing and forming equipment. The process is quite laborious and work intensive, so improving the actual glue lamp fabrication process is another ongoing effort in parallel to all of this. So on the right you can see the 3D scanning of one of the prototypes. And speaking about scanning, scanning was used in the process in mainly two ways. The first was to link the real fabrication space to the modeling environment so that we could position and monitor the workpiece in front of the spindle. And the second was as a way of verification and documentation. So that means to see the deviation between the made object and the model, but also as a way of kind of documenting the process and keeping track of the kind of the history of the objects that we've made. And this opened up the question of how an extended documentation of these sorts of prototypes can inform later models, not just for that specific project, but in terms of technique. So this sort of multi-scale modeling approach led to a proposal for the Tallinn Architecture Biennale based on the demonstrator that we were working with before. And what this method allowed us to do was to create quick design iterations while zooming in on specific elements and conditions. So this helped the success of the proposal because it allowed us to discuss the overall design on an architectural level while also discussing very specific fabrication issues with fabricators kind of in the same sort of way. And about the graph.
Yeah, just something to add. That's here in this case there was a direct link between the abstract graph that you see on the left and the 3D model. So for example, each line thickness was corresponding to members that were thicker, and the color code corresponding to the degree of centrality of each element, which we think could help us for assembly.
Yeah, and just to kind of finish off with some where the work has kind of gone in the meantime. So subsequently, Paul and I both pursued different aspects of this project in our own individual research projects. I've been looking more closely at this integration of scanning and sensing methods in glue lamp production with the help of my industrial partner. And this effort is looking at opportunities to use scanning and sensing to acquire useful material feedback that can better inform the production process. So to develop sort of soft fabrication models that are more adaptive and more kind of sensitive to what is actually going on in the process. But perhaps more interestingly, this also pursues the question I mentioned earlier of how material feedback could be documented, stored, and leveraged for future use. So in this way, it could present a sort of recorded experience that could inform how certain design decisions can have specific fabrication consequences. Yep.
And yes, and on my side, I've been actually looking at actually the other end of the spectrum where the data is actually produced. How do you actually navigate through this space where you end up with very intricate layer tables as design production is working with. So here you are in this interface, you're able to input a tag that's gonna search through the layers, which names contain this tag, and then display the object in your viewport.
Cool. Thank you very much.